I want to develop my node optimization model, where information makes voyages through nodes, choosing action in the current step, which enhance utility function of the whole system. What if we consider neuron like individual agent seeking its own utility? I can go deeper a little bit and construct a biology-inspired simple system. Neuron consists of several dendrites and axons. Dendrites receive information and make some computation in case of the connection. Neurons sums up data from its dendrites and passes further to axons after optional filtering, and the axons give info to the next neurons. Firstly, we count sparkling axons in each node. Sparkling means having information ready to passing. And yes, I use nodes for aggregation, and it's not necessary but might be useful later. Then we count active dendrites. It means not connected and searching the connection right now. After that, every active dendrite defines the most attractive neuron. Attractiveness negatively depends on the distance and positively on the node energy. Energy is the simple sum of working connections in the given node. Theoretically, energy is decaying by time. So, dendrite is attracted by a particular node and starts to move towards it, faster or slower. At the end of the time step, coordinates are renewed, and dendrite seeks connection in the closest node, if there are available sparkling axons. If all is okay, dendrite tries connection, receives information, processed it by internal function. In our example, the function is simple and without dynamic effects like in the real neurons. Utility function is computed. If it grows, connection is established, else abrupted. Now, internal utility function of the dendrite is equal to the system 1. But in general, it's not true. Functions are different, but for working effective systems, internal utility function depends on external, and external depends on positive and negative situations that happens after internal changes. It's important. The next time period cycle is repeating, assuming changes that happened to the last period. I construct only 2 neurons with 3 axons and dendrites plus 1 neuron with 1 dendrite for initial data and with also 3 axons. Internal function is the simple multiplying of the obtained signal by 1.1. Very small model, but it can map 3 to 4 only in 2 time steps. Magic. Then I made some enlargements. I added 1 neuron with 5 dendrites and 3 axons, but computing function is different. Now dendrite decreases incoming signal by 10%. Also, I have made inverted function that multiply information by -1. As you guess, 1 more neuron appears. Some changes are made in the internal kitchen of the axon and neuronal filtering for arrays. It needs if we have only 1 initial dendrite, and now it's the case. That trick widens model capability drastically. We can map, 3 to 10, or even -3 to 10, or array to array for revealing polynomial. Last case is not very impressive, but it's only 5 neurons and 16 possible connections with the increase and decrease by 10%. Not bad, I think. What does it give to us? I mean in theory. Like an annoyed voyage optimization model has a memory. It gives interpretability. With some upgrade, model can learn and make inference at the same time. Plus, there are myriads of ways to analyze nature at a different scale. Of course, we have plenty possibilities to improve our model. First of all, its dynamic aspect of energy flow and computation and dendrites, like in real life. Then we need more different functions in neurons and additional functions for cutting unused connection. We may scale the whole system. Couple of neurons are not sufficient, I think, and there are many things to do.